This is a walkthrough of a Further Maths A-Level Further Mechanics 2 paper. Question 1. A particle of mass 0.5 kg is attached to one end of a light elastic string. The other end of the string is attached to a fixed point O on a smooth horizontal surface. The string has natural length 2 meters and modulus of elasticity 8 newtons. The particle moves on the surface in a horizontal circle about O with a constant angular speed 1.5 radians per second. Find the radius of the circle. So a diagram of what's going on. So this is a view from the top. So here's the center O here. This purple line here represents the light elastic string, and this green circle here represents the mass. So what we're going to have is the tension of the string acting towards the center, and we're also going to have the acceleration acting towards the center as well. Okay, so let's write down what we know and what we have. Well, whenever we have circular motion, the acceleration is given by the radius times by omega squared, where omega is the angular velocity. We have the natural length of the string, which is 2 meters, so L is 2. We have the modulus elasticity, which is 8 newtons, 8. We have the mass of the particle, which is 0.5 kg, and we're told the angular speed, which is, so omega is going to be 1.5. So let's start by using Hooke's law to work out the tension in the light elastic string. So the tension is going to be lambda x over L. So that's going to be 8, and the extension is x over the natural length 2, so that gives us 4x. So now we're going to use F equals ma, and we're going to resolve towards the center. So we have T is equal to ma. So the tension, which we have, that's 4x. The mass is 0.5. And the acceleration, that's going to be the radius times by omega squared. So let's start to fill this in. So 4x is equal to 0.5. Now when it comes to the radius basically is going to be the length of the light elastic string, and the light elastic string is going to be an extension. So we're going to have its natural length plus the extension of x. That is going to be the radius of this circle. So let me write down over here, r, that radius is equal to 2 plus x. So when I come to do r here, I'll just put 2 plus x times by the angular speed, so 1.5 squared. Okay, let's see what we can get from that. So if I do the 0.5 times by 1.5 squared, that gives me 9 over 8. So I've got 9 over 8, 2 plus x. Let's expand the brackets because we want to solve for x, don't we? So 4x is going to equal to 9 over 4 plus 9 over 8x. So from there we'll take off the 9 over 8x from both sides. So 4 minus 9 over 8 gives me 23 over 8. So we've got 23 over 8x is equal to 9 over 4. So x, that's going to be 9 over 4 divided by 23 over 8. And that gives me 18 over 23. Now I need to find a radius, so that means that I can use this now that I know what x is. So the radius is equal to 2 plus x, which is 18 over 23. So that means that the radius is 2 and 18 over 23 meters. There we go. Question 2. Figure 1 shows a shaded template T formed by removing an isosceles right-angled triangle PQR from a uniform rectangular lamina ABCD. The rectangle has side AB of length 6A and side AD of length 5A. The triangle has sides PQ and PR of length 3A. The side PQ of the triangle is parallel to the side AB of the rectangle, and the distance between AB and PQ is A. Side PR of the triangle is parallel to the side AD of the rectangle, and the distance between PR and AD is A. Part A, show that the distance of the centre of mass of T from AB is 44 over 17A. Okay, so the first thing that I need to do, I'm going to create a table where the first column is going to have the shape, the second column the area of that shape, and then the last column the centre of mass, or the moments from AB of each shape. So in the first column here I've got the rectangle, and then I need to subtract from that, so a big subtraction sign here, the triangle like this. So in the second column I'm going to put the area. So the rectangle is just the width times the length, so 5A times 6A, so 30A squared. And then for the triangle, that's just the half the base times the height, so it's half 3A times 3A. So it's going to be 9 over 2A squared. Okay, so I'll just highlight those. Those are my areas of the two shapes. Next, I want the distance of the centre of mass from the line AB. So for the rectangle, from the line AB going across this way, because this rectangle is symmetrical, I just go halfway across. So 5 over 2A, that's going to be the distance of the centre of mass from AB. So just 5 over 2A. And then for the triangle, what I need to do is add together the x coordinates of the vertices and then divide by 3. So the coordinates of those vertices need to be the distances from the line AB. So this, or these two vertices here, are going to be a distance of A. So I've got two vertices that are a distance of A, and then the third vertex here, the distance from the line AB is going to be A plus 3A, so this is going to be a distance of 4A. So the three vertices together is A plus 4A. We divide that by 3 to find where the centre of mass of the triangle is in the x direction. So that's going to be 6A divided by 3. So that will just give me 2A. And I'll just highlight these numbers here because this is what I'm going to use. So the centre of mass from the line AB is x bar. So what I need is the area times the centre of mass for the rectangle, so that's 30A squared times by 5 over 2A. Now minus, because the triangle has been cut out of the rectangle, so minus 9 over 2A squared times by 2A. Let's just put these in brackets here. They don't really need to be in brackets. Then I divide that by the sum of the masses. So that's going to be the mass, or the area of the rectangle, minus the area of the triangle. So working this out, the numerator here is going to give me 66A cubed, and that's going to be all over 51 over 2A squared. And simplifying that, that gives me 44 over 17A as required. Let's carry on. The template T is freely pivoted at A. A horizontal force is applied to T at B so that T rests in equilibrium with AB vertical. The line of action of the force lies in the vertical plane containing T. Given that the weight of T is 85 newtons, part B, find the magnitude of the force exerted on T by the pivot at A. So the first thing I'm going to do is to draw a diagram of what's going on. So the orientation of the lamina is like this. It's actually in the same position as in figure 1, and we're told that it is freely pivoted at A. So that pivot is going to have a horizontal and vertical part to its reaction. So we'll just call that H and V. I'm assuming that they're going in these directions here. If I'm wrong, then I'll get negative values for here, for these values, H and V. There's a force applied at B that's keeping it horizontal. So I'll just put that here and we'll call that force F. And then I want to put on where the center of mass is. So I'll have a line going down here, and its mass is 85 newtons. Sorry, its weight is 85 newtons. And in part A, I worked out the distance from AB to that center of mass. So I know what this distance is here, and that is the 44/17A. So to find the magnitude of the force exerted on T by the pivot A, that's basically finding H and V. I'm going to start by taking moments about A, and that's going to allow me to find an equation that excludes V and H, and then I'm going to resolve horizontally and vertically. So taking moments about A, I'm just going to highlight what my moments diagram is going to look like. So I'm going to have this distance here and a force F pointing in that direction, and then this distance here, and then the weight like this. So I'll just draw that out over here. So imagine this is the point A here, and then we've got a distance that takes us to the force F, and that distance is the length of this edge here, which is 6A. And then I also have a distance to the 85. So let's go across, and we've got the 85 newtons going down. And this distance here is the distance to the center of mass from AB. So that's 44/17A. So these moments are balanced because it's in equilibrium. I've got a clockwise and an anti-clockwise moment. So my moments equation is going to be 6A times by F is equal to 44/17A times by 85. Now the A's will cancel out. So that equation will now become 6F is equal to 44/17 times by 85, which is 220. So from there I can work out what F is, divide both sides by 6, and I will get F, and I'll write its exact value, is 110/3. Now I'm going to resolve horizontally and vertically. So let's start by resolving horizontally. So if I do that, that will just be H is equal to F. H is equal to F, which basically means that this horizontal part of the this force here, or the magnitude, which we'll get onto in a moment. So H is just equal to 110/3. So let me just write that on here, 110/3. And then I'm going to resolve vertically. So that's just going to be V is equal to 85. So here we go. V is equal to 85. So I've got this 85 here. So now if I want to find the magnitude of the force that's exerted here, I just do Pythagoras on the 85 and 110. So I'll just write down magnitude of force exerted on T at A, capital letter A, is equal to the square root of 110 over 3 all squared plus 85 all squared. That gives me 92.57129, and it carries on like that. And I want to give this to 3 significant figures. That'll be fine. 92.6 newtons. Now I could give it to more accuracy because I haven't used G in my calculation, but yeah, 3 significant figures is the standard rounding for our answers. Question 3. A particle P of mass 2 kg is attached to one end of a light elastic spring of natural length 0.8 meters, a modulus of elasticity 49 newtons. The other end of the spring is attached to a fixed point P. Particle P hangs freely in equilibrium with P vertically below A. The particle is now pulled vertically down to the point B, where AB equals 1.4 meters, and released from rest. Part A. Show that P moves with simple harmonic motion about its equilibrium position. Okay, so my first step is going to be to draw out what's going on here. So I've got this point up here, and I've got this elastic spring. Okay, so let's draw my spring here. The spring is connected to a mass, which we're calling P, and its mass is 2 kg. Now it's currently in an equilibrium position, so let's call this equilibrium position. And so that equilibrium length is going to be made up of a natural length plus an extension, which we're going to work out. And in this equilibrium position, the tension pulling up is going to equal to the weight going down to G, and I'll just write down the other things we've been given. So L is equal to 0.8 and modulus elasticity 49. So as I said, what I'm going to do now is to calculate the extension of the spring at equilibrium. So that's T is equal to 2G, those forces are balanced. T is just going to be lambda x over L is equal to 2G. So we can put in a lambda 49, and x is actually this extension that we want to work out, divided by L, which is 0.8, is equal to 2G, that's 19.6. So we can now solve for E. So 19.6 times 0.8 divided by 49 gives me 8 over 25, or 0.32 meters. Okay, I'll just write down it as a decimal, 0.32 meters. Right, so we're now going to use our equation of motion. So the mass times the acceleration is equal to the forces. Now we are taking downwards as positive, so there's my acceleration, and I will have mg going down minus the tension trying to pull the mass up. So let's start to fill this in. M is 2, so we have 2a, 2 times the acceleration, is equal to 2g minus lambda x plus e, because it was at E before, and then we've got this extra extension. This is going to be this displacement above and below the equilibrium position. So lambda x over L. So from there I can put my numbers in. So 2 times the acceleration is equal to 2g minus lambda is 49, and then we have x plus the extension, so that was this 8 over 25, or 0.32, let's use 8 over 25, all over L, which is 0.8. So we'll sort out what's on the right hand side. So 2 times the acceleration is equal to 2g, and then we'll have minus, if you expand the brackets, 49 x over 0.8, and then if we work out what 49 times 8 over 5 divided by 0.8 is, we get 98 over 5, so minus 98 over 5. Now 2 times g is 98 over 5, so what's going to happen is these two will cancel out, and that will just leave us with, and now I'm going to divide both sides by 2 as well. X, the acceleration, is equal to minus 245 over 8x. Now, since this is in the form the acceleration is equal to negative omega squared x, p moves with simple harmonic motion. So let me write that down. So since this is in the form acceleration is equal to negative omega squared x, so where omega is going to be equal to the square root of this, which is 7 root 10 over 4, p moves with simple harmonic motion, or SHM, simple harmonic motion. Part B. Find the length of time in each complete oscillation for which P is more than 1.2 meters vertically below A. Now, to do this part of the question, we need the amplitude of the oscillation, and the oscillation is going to be about a length of L plus E, the natural length plus the extension, and the amplitude of that oscillation is going to be the difference between L plus E and 1.4. So let's work that out first, and then we can work out this amplitude here of oscillation. So first of all, since L plus E, the lateral length plus the extension, that's going to be 0.8 plus 8 over 25, or 0.32, and that's going to be equal to 1.12 meters. So basically that's going to be here 1.12 meters. Then we can say that the amplitude of oscillation, or the oscillation, should that be an A? Let's try again, let's try spelling again. Oscillation, here we go, is going to be equal to how much it's been pulled down to, 1.4 minus 1.12, and that gives us 0.28 meters. So that basically means that these distances here, 0.28 meters is going to be this bit here, and 0.28 meters is going to be this bit here. So moving up and down around this equilibrium position by a displacement of 0.28 meters from this equilibrium position. So I'll write that down. That's what A is, my amplitude. Now, also P starts at the end point of oscillation, so it's pulled down to this point here and then allowed to oscillate. So because it starts at this end point of oscillation when t is equal to 0, so basically down here, this is t is 0 at the very start, its displacement can be modelled by x is equal to the amplitude A times by the cosine of omega t. So if we fill in those numbers that we have, we'll have x is equal to the amplitude, that's 0.28, times by the cosine of omega. Now we've got omega from part A, so that will be 7 root 10 over 4 t. Now we want want to find the times when the length or the actual distance from A is 1.2 meters. That's this point here. Now that distance of 1.2 meters below A, we want to know what that displacement is from the equilibrium position. That's going to be our value of x here, which we'll use to find t. So 1.2 meters below A is an actual displacement from the equilibrium position of 1.2 minus 1.12 meters, which will give us 0.08 meters. So we now want to find the times when x is equal to 0.08, or the time when that happens. So we'll just write that equation down. So 0.08 is equal to 0.28 cos 7 root 10 over 4 t, and we're going to rearrange it so we can solve it. Dividing both sides by 0.28 gives you the cosine of 7 root 10 over 4t is equal to 2 over 7. So from there we can do the cos inverse of 2 over 7, so that will give us 7 root 10 over 4t is equal to 1.2810 and so on. So rearranging for t, I will get t is equal to 0.231486 and so on. So we've just worked out this time here. So I've like superimposed like one cycle, sort of just stretched it out so you can see what's going on. So if I just put a little asterisk by this, we've worked out this time here. Now it happens again over here. It's below 1.2 meters at this point here. Now all we need to do is to take this time that we found here and times it by 2, so that I know that it's going to be that length of time in a whole oscillation. So I'll take my value that I got there, times it by 2, and I will get t is equal to 0.46297. And as usual, let's give this to 3 significant figures. So this will be t is equal to 0.463 seconds. So that's going to be the time for which this particle, this mass, is at least 1.2 meters below this point A at the top. Question 4. A solid right circular cone has height 30 meters and base radius 5 meters. The cone is modelled as the solid generated when the solid region in figure 2 is rotated 360 degrees about the x-axis. The cone is non-uniform, so that the mass per unit volume of the cone at point xy is x over 100 kilograms per cubic meter, where x is greater than or equal to 0, less than or equal to 30. Part A show that the mass of the cone is 225 pi over 4 kilograms. Okay, so the first thing I'm going to do for part A is just to draw what this volume of revolution is going to look like. So I'm going to get a cone that's going to look something like this as it gets rotated around the x-axis. I'm going to need the equation of this line, and I'm going to need the formula I'm going to use to find the mass. So let's write down the formula first. So mass, which I'll use as m, is going to be equal to the integral between my limits of a and b of rho, and that's the density, times by pi times by y squared dx. So I need y to find y squared. So let's find the equation of this. So y is going to equal to, it's just a straight line here, the gradient over the intercept, where the intercept is 0. The gradient That will be the change in y over the change in x, so that's 5 over 30x, which I can simplify to 1/6 x, or x over 6. Right, so the mass is going to be equal to limits of 0 and 30. They're the two x values at the end. Times by rho. Now rho is the density, and we're given a density here, x over 100. So x over 100 times that by pi, times that by y squared, so that's x over 6 squared dx. Let's bring all of the constants across. So I've got divide by 100. This is going to be x squared over 36. I'm also dividing by 36. So I'll be dividing in total by 100 times 36, which is 3,600. And I've also got a constant of pi here, which I'll take across. So all of my constants is going to be pi over 3,600. Again, limits of 0 and 30. Let's try and tidy this up as much as we can. So we've got x here times by x squared. So I'll have x cubed dx. So we've got a nice straightforward integration. So you've got pi over 3,600. Then x cubed differentiated will be integrated, sorry, will be x to the power 4 over 4. Limits of 0 and 30. Let's put those in and see what we get. So pi over 3,600, and that's going to be times by 30 to the power 4 over 4 minus 0 to the power 4 over 4, basically 0. So that will give me pi over 3,600 times by 30 to the power 4 over 4, which is 202,000. Sorry, I just dropped my calculator there. 202,500. So 202,500. When we multiply that out, that will basically give us 225 over 4. That's times by pi. So 225 pi over 4 as required. Okay, so we've got the answer that they wanted. Part B. Find the distance of the centre of mass of the cone from its vertex. Okay, so the first thing is to recognise that since we have the mass times the centre of mass is equal to the integral between limits of a and b of rho times by pi times by y squared x dx, we can rearrange this to get the centre of mass. So I'll have the centre of mass is equal to that integral, rho pi y squared x dx, divided by the mass. And that's quite handy because we worked out the mass here, or we proved that the mass in part A was 225 divided by 4. Okay, let's get substituting. So the centre of mass is going to be equal to, now integral is limits of 0 and 30. Rho is x over 100 times by pi times by y squared. So that's going to be x over 6 all squared. So x over 6 all squared. Let me just draw like a line here just to separate out what's above. Actually, rather than do that, let's just move it down a little bit, and that'll probably be a little bit easier to see. So let's just go down here. So x bar is equal to 0 and 30 here. We said the density was x over 100 times by pi times by x over 6 squared times by x dx, and we're dividing that by the mass, which we know is 225 pi over 4. Right, let's start to tidy up what we have at the top here. So I think there are going to be some constants I can bring across. I've got 100, I've got pi, I've got the dividing by 36 and dividing by 100. So I'm going to have pi over 3,600 as my constant, brought across, still 0 and 30. That will leave me with x times by x squared times by x. So that will be x to the power 4 dx all over this 225 pi over 4. So the top nice and easy to integrate, so pi over 3,600, and then x to the power 4 becomes x to the power 5 over 5 with these limits of 0 and 30, all over 225 pi over 4. If we put the limits in, pi over 3,600, and then it'll be 30 to the power 5 over 5 minus 0 to the power 5 over 5, basically 0, all divided by 225 pi over 4. Okay, so at the top we're going to get 1,350 pi divided by this 225 pi over 4, and if we do that we get an answer of exactly 24. So let's do it here. X bar is equal to 24, and this was in meters, this one. Question 5. For a particle above the surface of the Earth at a distance x from the centre of the Earth, the magnitude of the gravitational force acting on the particle due to the Earth is inversely proportional to x squared. At the surface of the Earth, the acceleration due to gravity is g. The Earth can be modelled as a fixed sphere of radius r. A particle p of mass m is at a point that is at a distance x minus r above the surface of the Earth. Part A showed that the magnitude of the Earth's gravitational force acting on p is mgr squared over x squared. So the first thing I want to do is just a diagram showing what's going on. So here, this is the Earth. This is the centre of the Earth here, that little dot. The radius of the Earth is r. And then we have this particle that's above the Earth's surface. So we'll have this particle up here. And the distance from the centre of the Earth, or actually the distance from the mass to the surface of the Earth. Okay, so this distance here is x minus r, which means the distance of the particle to the centre of the Earth, so this distance here, will be x. And there's going to be a force acting on that particle that's directed towards the centre of the Earth. Now, first of all, if that particle were on the Earth's surface here, then the magnitude, the size of that force acting towards the centre of the Earth would be mg. So mg would be equal to F. We're told that that force F is, and it's up here somewhere, is inversely proportional to x squared. So what that means is, let's just put my arrow showing it's going towards the centre of the Earth, that force is going to be inversely proportional to this distance to the centre of the Earth, and on the Earth's surface that will be r. So it'll be k over r squared. That's the distance of the particle to the centre of the Earth when it's on the Earth's surface. We can put these two equations together because they're both equal to F, and I will have mg is equal to k over r squared. That means that I can rearrange this to find the value of k, and k is going to be equal to r squared mg. So now that we have this value of k, we're going to consider the particle at a distance of x up here from the centre of the Earth. Now that force acting on a particle, it's still inversely proportional to the distance squared, but at a distance of x, that's going to be k over x squared. Now we can replace k with what we've worked out before, so F is equal to r squared mg over x squared as required. That's what we wanted. I guess the only difference is the way in which I've written this. You could write the mg first and then r squared, but we've shown that the magnitude of the Earth's gravitational force acting on P is this value here. Okay, a rocket is fired vertically upwards with speed u from a point on the surface of the Earth. When a rocket is at a height 2r above the surface of the Earth, the speed of the rocket is the square root of g times r. The rocket is modelled as a particle of constant mass m, and the Earth is modelled as a fixed sphere of radius r. All forces acting on the rocket, other than the Earth's gravitational force, can be ignored. Part B, find an expression for u in terms of g and r. Okay, so the first thing I'm going to do is just a little diagram here. This is the Earth. This is the particle up here. And I'm going to be taking upwards away from the Earth as positive and using F is equal to ma. And the force that's on the particle is going to be negative mg r squared over x squared is equal to ma. I can replace a with v dv dx. So then I will have negative mg r squared over x squared is equal to m times by v dv dx. The m's are going to cancel out, so we can get rid of those. We could have done that at the previous step. So I've now got negative g r squared over x squared is equal to v dv dx. So I'm going to solve this by separation of variables. So if I take or multiply both sides by dx, so negative g r squared over x squared dx is equal to v dv. So I'm going to stick a big fat integral sign in front of both sides like this. I'm going to move my constant across, so that's negative g r squared, because the radius of the Earth and g are constant, and so I'll be integrating 1 over x squared with respect to x, and then the other side v with respect to v. So that will give me negative g r squared, and then 1 over x squared is going to become negative x to the minus 1, or negative 1 over x, and then half v squared plus c. So I can see that my negatives will cancel out here. And so my next job, once I write this out, is to calculate the value of this constant. So I could actually write this as gr squared over x is equal to half v squared plus c. So the way that I'm going to do that is to look at the information that's given, and I've got that when the speed is 0, that is on the surface of the Earth. Right, so I have v is equal to u, and when the rocket is on the surface of the Earth, that will mean that its distance from the center of the Earth is r, so x is equal to r. So let's go over here and put those values in, and we're going to work out the value of the constant. So we'll have gr squared over x, which is r, is equal to half u squared plus c. So I can see that the r's are going to cancel out. So this basically leaves me with a constant c equal to gr minus half u squared. So this constant can now go here, and that will give me a value of g over r squared over x is equal to half v squared plus my constant, which is gr minus half u squared. Now the question says that I need to give my answer in terms of g and r, so I need to eliminate any v's, and I can do that with another piece of information that's given in the question, which says that when the rocket is at a height of 2r above the surface of the Earth, the speed of the rocket is root gr. So I can make a couple of substitutions here. So when the speed of the rocket. So when v is equal to root gr, the height of the rocket is 2r above the surface of the Earth. Its distance x from the center of the Earth is going to be 3r. So I'm now going to make those substitutions. So I'll have g over r squared, or sorry, gr squared. I think I said g over r squared before, but I meant gr squared over x, so x is 3r, is equal to half v squared, so v is this root gr, and that's going to be squared, plus gr minus half u squared. And the rest of this is just about making u squared the subject. So let's start, or u the subject. Let's start by making half u squared the subject. So that means this has moved across over here. So this will just give me a half gr, and then plus gr. And then when I move this across, where the r's cancel out here, I will have minus gr over 3. So minus gr over 3. So if I put all of these grs together, I'll actually get 7 over 6 gr, and then times both sides by 2, I'll get u squared is equal to 7 over 3 gr. So that means I can write u is equal to the square root of 7 over 3 gr. Okay, let's highlight that, and then let's look at the final part of this question. And it just says, suggest one way in which the model could be refined to make it more realistic. Okay, I've given 3 here. You could possibly think of more. It's only 1 mark, so you only need one of these. So for example, we could consider air resistance. It does say that we're ignoring all other forces. Air resistance would be important. We could decide that we're not going to model the rocket as a particle. A rocket is big enough and ugly enough to be modeled as something other than a particle. And also rockets, they carry an awful amount of fuel, and this fuel is going to get used up as the rocket goes up into space. So the mass of the rocket is going to decrease, so we might want to include that in our improved model to make it more realistic. Question 6. A particle P is moving along the positive x-axis in the direction of x increasing. When the displacement of P from the origin O is x meters, the velocity of P is v meters per second, where v is equal to 9 minus 3 over x. X is greater than or equal to 1. At time t equals 0 seconds, x equals 1. At time equals t seconds, x is equal to 3. Part A, find the acceleration of P when x is equal to 3. Okay, so the first thing, let's just write down what we've been given. V is equal to 9 minus 3 over x. Now, we know that the acceleration A can be written as v dv dx. And I can find this dv dx part by differentiating what I've been given. So dv dx, if I differentiate, so the 9 is going to disappear. The negative 3 over x I could write as negative 3x to the power negative 1. So if I differentiate that, I'll be multiplying by negative 1, so it'll become positive, and then it will be x to the power minus 2. I'll write that as 3 over x squared. So now I'll write the acceleration is v, and v is 9 minus 3 over x, times by dv dx, which is this 3 over x squared. Okay, so a is equal to v, which is this, which was given in the question, times by dv dx, which is this 3 over x squared, which is what I got when I differentiated v. What I'll do now is I will expand the brackets, and I'll have the acceleration is equal to 27 over x squared minus 9 over x cubed. Now the question says when x is equal to 3, so I now sub in 3, so sub in x is equal to 3, and if I'll do that, what I'll get is a is equal to 27 over 3 squared minus 9 over 3 cubed. That becomes 27 over 9 minus 9 over 27, and that's equal to 8 over 3 meters per second squared. So there we go, I've got my answer for part A. A is equal to 8 over 3 meters per second squared. So I'll highlight it here, and I'll highlight my working here as well. Moving on to part B, and it says show that t is equal to 2 over 9 plus 1 over 27 log 4. Okay, so let's start with what we've been given, which is v is equal to 9 minus 3 over x. Now we know that if we differentiate the displacement with respect to time, we get the velocity. So v is equal to dx dt. So I can write the statement that's given as dx dt is equal to 9 minus 3 over x. Now I'm going to use the separation of variables to solve this differential equation. So that means collecting like terms, putting the t terms on one side and the x terms on the other. So I will have dx dt is equal to, now if I'm going to keep these terms together, I want it as a single term. So I'm going to write 9 as 9x over x minus 3 over x. I need a single term over here so that I can separate out the variables. So that will give me dx dt is equal to 9x minus 3 all over this common denominator of x. Now I can separate out the variables now that I've got a single term, and that will give me x over 9x minus 3 dx is equal to dt. Now that dt is like 1 dt, and I can put an integration sign in front of both sides to integrate it. Now to integrate this is partial fractions here, and I need to work out what this is written as partial fractions. So basically I want to write x over 9x minus 3. Now since the numerator is of the same degree as the denominator, that's an improper fraction, so I want to write it in the form a plus b over 9x minus 3. So that's going to be my job now, to work out the values of a and b, and we'll do that over here. So to make the denominators the same, I will end up with x is equal to a times by 9x minus 3 plus b, and then if I compare coefficients to both sides, let's compare the coefficients of x, and then I will get 9a is equal to 1, which means that a is equal to 1/9. And then if I compare the number coefficients, so compare the coefficients of the numbers. Now on the left hand side I've got no number, so it's basically 0, but on the other side I will get b minus 3a is equal to 0, and from this I will get b is equal to 1/3. So b is equal to 1/3. I'll just highlight those because those values are going to give me my partial fractions. So I can go back to what I have here, and this integration will now become, on the left hand side, integrating a, that's 1/9, plus b over 9x minus 3, so that's plus 1/3, over 9x minus 3 dx is equal to 1 dt. Now what I'll do now is I'm going to times everything by 9 just to get rid of these nasty fractions here. So then I'll have 1 plus, and then it'll be 3 over 9x minus 3 dx is equal to, times the other side by 9 as well, 9 dt. And I can also now cancel down this fraction here. I can divide everything by 3. So I'll basically get 1 over 3x minus 1, and that's what I'm going to integrate. So yeah, I'll do that now. So the 1 integrated with respect to x, that will just become x, and then basically the 1 over 3x minus 1, so it's going to be log, so let's have a look. If I do log of the bottom, so log of 3x minus 1, I will need to adjust by dividing by a third, because I don't want 3 at the top, I want 1, and that's going to equal on the other side 9t plus my constant of integration c. Okay, so I'm now going to use the t equals 0, x equals 1 to find c. So I'll just put that in brackets down here. T equals 0, x equals 1, and I'll substitute those in to find my constant of integration. So that will give me 1 plus 1/3 log, and then I will have 3 times by 1 minus 1, so that's 3 minus 1, 2. So natural log 2 is equal to, well, the 9 is going to go, because you're going to be doing 9 times by 0. So that's what c is. So my full expression now for my solution is going to be x plus 1/3 log. Now I could actually put the 3x minus 1 in brackets, because this is going to be positive because x is greater than or equal to 1, so I don't need to do the modulus of that. It doesn't make any difference whether you put the modulus or not. Is equal to 9t plus c, and c is 1 plus 1/3 natural log 2. So now I'm going to sub in that t is equal to t, big T, and x is equal to 3 into my full expression here. So what will I have? X becomes 3, so 3 plus 1/3 natural log, and then we'll have the 3 going here, so 3 times 3 minus 1, so that's going to be 1/3 log 8, is equal to 9 times by big T plus 1 plus 1/3 log 2. Okay, let's make a little bit of space up here at the top so we can now finish off the working for this. I believe now the rest of this question is just going to be simplifying that expression that I've now got. Okay, so let's start by making 9t the subject. So I'll have 9t is equal to, so I'm going to take away 1 from both sides, so that will be 2, and then I'll have 1/3 log 8 minus 1/3 log 2, so plus 1/3 log 8 minus 1/3 log 2. Now we need to keep an eye on what we're trying to get to, so there's no point doing particular things unless we're heading towards this type of answer. So I can see that I need to divide both sides by 9. We'll do that in a minute, but let's put these two logs together. So what that will give us is 9t is equal to 2 plus, we can take out a third, and then in brackets we'll have log 8 minus log 2. Now the log 8 minus log 2 is like log 8 natural log 8 divided by 2, so that's going to be log 4. So I have 9t is equal to 2 plus 1/3 log 4. Now we'll divide both sides by 9, and we'll have t is equal to 2 over 9 plus, and 1/3 divided by 9 becomes 1/27, log 4 as required. Question 7. Figure 3 shows the shaded region R bounded by the curve with equation y is equal to 1/square root of 16 minus x minus 4 all squared. The x-axis and the lines with equations x equals 2 and x equals 7. A uniform solid of revolution S is formed by rotating R through 360 degrees about the x-axis. Part A, show that the x-coordinate of the centre of mass of S is 8 log 6 over log 21. Okay, so let's start by reminding ourselves of the formula for the centre of mass. Remember, this shape is being rotated around the x-axis here. So x bar is going to be equal to the integral of pi y squared x dx over the integral of pi y squared dx. So let's start by working out the top part here, the integral of pi y squared x dx. Right, so let's start by bringing across the constant, which is going to be pi. And so we've got y squared, so that's going to be 1 over the square root of 16 minus x minus 4 all squared. And that is going to be squared, so there's my y squared. That's going to get times by x dx. So we'll carry on down here and simplify that. So if I'm going to square this, I'm going to get 1 over, and then I get rid of this square root. So it's going to be pi times by the integral of 1 over 16 minus x minus 4 all squared times by x dx. So I can put that x at the top like that. My next step would be to multiply out the brackets at the bottom. So I'll have 16 and then minus x squared minus 8x plus 16. So that's all going to be subtracted. So let's simplify that at the bottom. So we'll get x over. Now I'm going to take the minus across here like this. So I'll now have x squared. Now I would have had plus 8x. So it's going to be minus 8x. And the 16 minus 16, that cancels out. So it's now about finding this integral here between these limits of 2 and 7. Now every term has got x in it, so I can divide everything by x. So I'll just have 1 at the top, and I'll just 8 and x minus 8. So now we have an easier integral to do. Mustn't forget about that minus sign. So minus pi, and so that will be 1 over x minus 8 dx. That should be a nice straightforward one to do. So that's basically just going to be log of the bottom here. So log of natural log of x minus 8. So pi times by negative pi times by the log natural log of x minus 8, and then between these limits of 7 and 2. So let's substitute those in. So we've now got negative pi times by log of, so 7 minus 8 is going to be negative 1. Now I'm not going to panic, and I can't do the log of a negative number, but I'm sure there's going to be some simplifying at some point that's going to get rid of these negative numbers. And then log of, and then it's going to be 2 minus 8, so negative 6. Because it's a subtraction, that can all go together. So I've got negative pi, and then basically I've got the natural log of negative 1 divided by negative 6. So I knew I didn't need to panic, because that now becomes the natural log of 1/6. And then I can deal with this negative here, make it a power. So from there I will get pi, and then I get 1/6 to the power negative 1, so that becomes pi log 6. So let me park this answer up here. So pi log 6, So that's what I've got for the top part, and now I'm going to work on the bottom part. So let me just clear off this work and create a bit of space. Okay, so it's going to be pi. So I've just moved the constant across like I did before, and then y squared, so 1 over the square root of 16 minus x minus 4 all squared, and all of that gets squared, not times by x this time, just dx. So let's tidy that up and see what we get. So obviously if I'm squaring that fraction, that gets rid of the square root at the bottom, and the top is just 1, like this. Next step now would be to expand those brackets at the bottom. So I could actually use the working that I had from before. That would be very useful. So 16 minus, and then x squared minus 8x plus 16 dx. And I think I'll do the same thing as I did before, which is to take the negative across as well. I just prefer a positive coefficient of x. So I'll now have 1 over, so the negative x squared will become positive x squared, and then this would have been positive 8x, so it's become minus 8x, and the 16 cancel out. Now if I factorize the bottom, this is going to need partial fractions to be able to integrate this. So I'll do my partial fractions working up here. So I know I want to write it in the form 1 is going to be equal to a over x plus b over x minus a. I'm sort of just going to speed this up. I know it's actually not going to be equal to 1 because I've got that denominator, but I know that I'm going to have a times by x minus 8, and then I'll have b times by x. Okay, let's compare coefficients. So if I compare the coefficients of x, so obviously on one side it's 0, so there's no x terms on this side. Then on the other side I'm going to get 0 is equal to ax, or a plus b. Then if I compare the number coefficients, I've got 1 on the left hand side, and then on the right hand side I will get negative 8a. So that allows me to work out a and b. So a is going to be equal to negative an eighth. If I just divide both sides by negative 8, and since a plus b are 0, that means that b is equal to positive 1/8. So if I now put those in, so I've got negative pi, and I will have basically negative 1/8 over x plus 1/8 over x minus 8 dx. Next I'm going to take over negative 1/8 as a constant, so I'll get pi over 8, so I'm taking negative 8 across, and that will give me 1 over x minus 1 over x minus 8. So that's going to be a fairly straightforward integration. So pi over 8, 1 over x becomes log x. And then if I were to do log at the bottom, I would get a positive 1. So it's going to be minus log x minus 8. And then I need to put in my limits of 2 and 7, just like before. I guess I could have put limits all the way through this here. These limits 2 and 7, 2 and 7, as long as I put those limits in at the end. Okay, just close these brackets here, and let's see what we get now. So pi over 8, and then put 7 in, so it'll be log 7, actual log 7, minus, and if I put 7 in here, so that'll be minus log negative 1. Okay, so that's the first bit, and then minus, and I'll put the 2 in, so that'll be log 2, and then minus log negative 6. Okay, so let's simplify all this now. So here I would get the log of 7 divided by negative 1. So log of, and I'm going to put it all together in 7 divided by negative 1. And then that's going to get divided by the log of 2 divided by negative 6. So 2 over negative 6. What does that give us? Pi over 8. And we get natural log 21. So now I can park that answer up here, take this away, and my second bit is pi over 8 log 21. So now I need to do the top one divided by the bottom one. So our centre of mass, x bar, is going to equal to pi log 6 divided by pi over 8 log 21. Now the pi's will cancel out, and dividing by 1 over 8 is the same as timesing by 8. So I'll get 8 log 6 over log 21 as required. The solid S is placed with its smaller plane face on an inclined plane that is at an angle alpha to the horizontal. The inclined plane is sufficiently rough to prevent S from sliding. Given that S does not topple, part B, find the greatest possible value of alpha. Okay, so let's draw a diagram of what's going on. Now, hopefully this will sort of illustrate the type of shape that we have once this region here has been rotated around the x-axis. We've calculated the centre of mass, and it's going to be this face here that I'm shading in blue, which is going to be in contact with the plane. So this is my attempt to try and draw what this 3D shape will look like on this plane with the centre of mass. We found the x value of the centre of mass, and I want this line here to be inside the shape, to go right through the corner to find like this maximum angle alpha. So I've zoomed in on it a bit. So imagine this triangle here, that's where the centre of mass is. I want to find this angle, so I need to find at least 2 of the lengths in this triangle here. Now in part A, I found the centre of mass, which was this 8 log 6 over log 21. And that's about 4.7 something. So it's going to be, I don't know, roughly at this point here. And I need to know how far up is that centre of mass from this bottom face, which is in contact with the plane. So the plane is actually here. So this is where the plane would be. So if I can find this distance here, so I've got this centre of mass, let's write it down. So this is the 8 log 6 over log 21. That is going to be the same as this distance here, which is this distance. So this 8 log 6 over log 21 is the distance from the origin. Now I've got this bit here too, which I need to subtract to find the sort of actual distance from the base of the shape. So this side of the triangle, which represents this length here, that is going to be 8 log 6 over log 21 minus 2. Let's get rid of that. So minus 2. So we're subtracting this bit here because we only want to know this length here. Now, I could also find this length here. Now, this is the length that's going down the centre along this part. Let me highlight it maybe in a different colour. So if I highlight it in yellow, so this length here is actually the same as this length here. Now to find that length, what I need is the y coordinate at this point, and to do that I can just get the x coordinate of 2 and substitute it into here. Okay, so let's do that. So when x equals 2, we will have y is equal to 1 over the square root of 16 minus, that'll be 2 minus 4 all squared. So that'll be 1 over the square root of 16 minus, so 2 minus 4, negative 2 squared is 4. So that just becomes 1 over root 12. So then that is the length of this side, 1 over root 12. So I've got this length here, 1 over root 12. I've got this length here, 8 log 6 over log 21 minus 2. So I can now find that angle alpha, because remember that angle alpha there is going to be the same as the maximum incline. So max value of alpha, that's going to be when this line of action goes through the corner of the shape, and that will be when we get a diagram that looks like this. And the tan of that angle, because we have the opposite and the adjacent to that angle, is going to be the opposite, so 1 over root 12 divided by 8 log 6 over log 21 minus 2. So we're going to put all of that in our calculator and actually do the tan inverse of that to find alpha. And from my calculator in degrees, I get 6.08446 and so on. We want to give that to 3 significant figures, so 6.08 degrees, and that's, as I said, to 3 significant figures. So that's going to be the maximum angle at which I can incline this plane before the shape starts to move, and it's, well, basically it's going to slide, not topple. Question number 8. Figure 4 shows a smooth solid hemisphere with radius A and centre O fixed with its circular plane face on a horizontal surface. A particle P of mass m is slightly disturbed from rest at the highest point on the surface of the hemisphere. When OP has turned for an angle theta, the particle is still on the surface of the hemisphere, and a normal reaction between P and the hemisphere has magnitude R. Part A, show that R is equal to mg times by 3 cos theta minus 2. Okay, so I'm going to draw here what's going on. So we start with the particle P on top, and then it moves around by an angle of theta, and then it ends up here. So I'm going to use energy to answer this question. So I'm going to work out the total energy we have up here, and then the total energy when we get round to this point. So at this point here, it's disturbed from rest, so the kinetic energy is 0. To potential energy, well, I'm going to take the plane as a point of 0 potential energy. So the height that the particle is initially is going to be A. So its kinetic energy, potential energy is mgA. Then when it gets disturbed and it moves around by an angle of theta, the kinetic energy is now half mv squared. So it's now moving with a particular velocity, but now its height has changed. It's now lower than it was before. So it's now mg times by, and the height that we want is going to be this height here. Let me mark that in like a purple line here. So we want to work out that height. Now we've got an alternate angle here, so that means that we have this angle here. Let's just highlight that in yellow or something. So the angle here and the angle here, they're the same. And if I sort of zoom in on what I've got here and just draw it like a little bit bigger, so this is the height I want to find. The hypotenuse here, that's the radius of the hemisphere, which is A, and then we have this angle here, which is theta. So the height of the particle at this point is going to be a cos theta. So that's this height here, a cos theta. So potential energy, let's give myself a bit of space, is going to be equal to mg times by a cos theta, and that's because this h here is equal to a cos theta. Now, using the conservation of energy, no energy is lost. The total energy that I have initially, which is mga, is going to be equal to the total energy at this other point, as it's still in the hemisphere, which is half mv squared plus mga cos theta, and I'll be able to cancel out all of the m's here. So that gives ga is equal to half v squared plus ga cos theta, and I'm going to rearrange this to make v squared the subject, because it's going to be useful in a moment, and that will give me 2ga, and then factorising the 2ga, I'll have in brackets 1 minus cos theta. So I'll just highlight that because I will be using that in a moment. And then the next thing I'm going to do is resolve in a direction which is parallel to PO. So another little drawing here. Here's my particle on the hemisphere. There's going to be a normal reaction R here, which is like perpendicular to the tangent of the particle where it's in contact with the sphere. mg going down here like this, and parallel to R, I'm going to have mg cos theta, which is going to be over here. Mg cos theta, that's because this angle here is theta, and that corresponds to this angle here, which is this angle here. And because I've got circular motion, the acceleration is going to be directed towards the centre, and that acceleration is going to be v squared over r. Now, since the radius is a, that's going to be v squared over a, but I'm not going to write that because I don't want to confuse the a for acceleration with the a which is used for the radius. Okay, so resolving in this direction, which is parallel to PO, I will get mg cos theta, then minus r, because that's going away from the centre, is equal to ma, and that a is equal to the v squared over the radius, and now I'll put the a in here. Now I'll rearrange this to make r the subject, and I will have r is equal to mg cos theta minus m v squared over a. That can all be over a, or just the v squared over a. And now I'm going to substitute in what I've got for v squared up here, and that will give me r is equal to mg cos theta minus, and then multiplying this by m, that's my v squared, that will give me 2mga times by this 1 minus cos theta, and that's over a. So I've just substituted in this for v squared here. The a's will cancel out, so let's cancel those out, and then from there we will get r is equal to mg cos theta minus 2mg plus, and I'm expanding the brackets here, 2mg cos theta, and then I can refactorize it, and I'll have r is equal to, take mg out because that's common to every term, and then I've got cos theta plus another 2 cos theta, so that's going to be 3 cos theta, and then minus to 2mg, so minus 2. So I get the result that they want as required. Part B. Deduce the value of cos theta when P loses contact with the hemisphere, giving a reason for your answer. Well, I'm going to give the reason first, and the reason is going to be that when P loses contact with the surface, the normal reaction R is going to be equal to 0 because it's not touching it anymore. So if R is equal to 0, that means that this here is equal to 0. So mg cos, or 3 cos theta minus 2 is equal to 0. Now mg cannot be equal to 0. So that means that 3 cos theta minus 2 is equal to 0. Move the 2 across, divide by 3. And so we have cos theta is equal to 2/3. And part C, find the direction of motion of P at the instant when it hits the horizontal surface. So first of all, when P leaves the surface, it becomes a projectile. So let's draw out what it's going to look like. So I'm going to have my hemisphere here, and then P, and as it leaves the surface, it's going to be a projectile and have this type of motion and hit the ground. And what we need to do at this point here is to work out the angle at which it hits the ground. So we want to know the horizontal and vertical components of the velocity, or at least two components of the velocity, even if that's the sort of actual direction here, so I can find the horizontal and vertical parts. Okay, so let's start by finding out what this velocity is at the moment that it leaves the sphere, v. So let me just draw out one part of a right angle triangle here to find out what's going on with the velocity at the start as it just leaves the sphere. So I want to find this v here. Now I can do that because I can use v squared equals 2ga times by 1 minus cos theta to work out what v is. So I basically want to know, or need to know, what that velocity is. Well, I want to know what the angle is first of all. So this is my A, and I have my theta here. Now I already know that this angle here is theta. Now this line here corresponds to this part of the triangle, and so the line I'm going to draw here is like the radius. So I've got an angle theta here, which means that this is an angle theta here. So once I find v, I know that over here I'm going to have v sine theta, and over here I'm going to have v cos theta. So we're now going to be finding v when cos theta equals 2/3. So when cos theta is equal to 2/3, that means that v squared is equal to 2ga times by 1 minus 2/3. So that's going to be 2ga times by 1/3, and so v squared is 2/3 ga. And if I square root that, I will get v is equal to the square root of 2/3 ga. So let me add that to my little triangle over here. So I'll take out the v and replace it with square root of 2/3 ga. Now I know this angle here, or the cosine of that angle, so I can then work out this horizontal component of the velocity. So that will just be the square root 2/3 ga, and that's going to get times by cos theta, which is 2/3. So actually let me write that as 2/3, I'm doing the same colour, 2/3 root 2/3 ga. Now for the sine theta, let me just do a triangle here. So I've got my theta, 2/3, so that's going to be 2, 3 for the hypotenuse. So if I do 3 squared 9 minus 4, that's 5. So this is going to be √5. So that means that sine theta is going to be √5/3. So now I can write down what the vertical part of the velocity is here. So that will be √5/3 times by this. So let's write that down. So √5/3 times by the square root 2/3 GA. Now this horizontal velocity here, this is constant. So when it hits the ground, it's going to be the same amount. And what I'm going to do, I'm going to use suvat to work out the vertical velocity when it hits the ground. Now, this isn't the only way of doing this. I could also use kinetic energy and use the kinetic energy to work out this velocity when it hits the ground. And actually, I might show both ways. So I'll start by doing the suvat way, taking downwards as positive. So I'm not interested in time. Acceleration downwards is going to be g. S. Now S is going to be the distance that this needs to travel downwards to hit the ground, and that's going to be this distance here. So A cos theta, A times by 2/3, so 2/3 A is the distance it needs to move down, 2/3 A. U, well, that's going to be this velocity here. It's like initial velocity. So √5/3 times by square root 2/3 GA, and we want to find V. So that's going to be V squared is equal to U squared plus 2AS. So V squared will equal U squared. So all of this here is going to get squared. So that will be 5/9 times by 2/3 GA. So that's my U squared plus 2 A, which is G, times by S, which is 2/3 A. If I simplify all of that, I will get V squared is equal to 46/27 GA. If I square root it, that will give me V is equal to the square root of 46/27 GA. So this is the situation I've got. I've got a projectile approaching the ground like this, and I've now got the horizontal and vertical components of the velocity, and I'm going to find the angle that it makes with the horizontal. The horizontal velocity, because it's constant, that's this 2/3 times by the square root of 2/3 GA, and the vertical velocity, well, that's just what I've worked out here, this square root of 46/27 GA. So that angle, which I'm calling theta here, let me give it a different name because I've got theta already. Let's call this beta. Sorry, I accidentally took my thing out there. So yeah, let's call this angle here beta. So what if I've got opposite and adjacent? So tan beta is going to be the opposite. So square root 46/27 GA, so that's all square rooted, over 2/3 times by the square root of 2/3 GA. Now the root GA at the top and the bottom all cancel out, and then I can work out beta by doing a tan inverse of what's left, and that gives me 67.326 and so on degrees. So I'll give the answer to 3 significant figures. So that'll be, sorry, not 26, I think it's 67.326 3624, sorry, like that. So yeah, it'd be 67.4 degrees. So let me put the answer up here, 67.4 degrees, 3 SF. I'm also going to show you the other way of doing this question if you're going to be using energy and not use SUVAT. Okay, so if I'm going to do it the energy way, I don't need this component, the vertical component, so I wouldn't need that triangle that I had before, because I'm not going to be using SUVAT. Using the conservation of energy, the energy that I start with, which is only going to be potential energy MGA, is equal to the energy that I have on the ground. There's going to be no potential energy, only kinetic energy, so half mv squared. Basically want to find out what v squared is. It basically gives me what this part of the triangle is when it hits the ground. The m's cancel out, so let's get rid of those. And then if I rearrange it, that's going to give me GA is equal to half v squared times both sides by 2. That will give me v squared is equal to 2GA, square root it, v is equal to the square root of 2GA. So what I've got now with my triangle as it hits the ground are two parts. So I've now got this is root 2GA because I've got the speed when it hits the ground. Sorry if I keep mixing up speed and velocity, but I've got the speed when it hits the ground here, this hypotenuse part, and this horizontal one, because that was constant anyway. So 2/3 and then root 2/3 GA. And then to find this angle here, the same angle that I had before, rather than doing tan, because I've got the adjacent and a hypotenuse, the cosine, actually let's call it beta like I did before, the cosine of that angle, beta, rather than tan, because it's not opposite, vertical and hypotenuse, horizontal like before, horizontal adjacent as before, opposite adjacent, vertical, horizontal. It's going to be the adjacent, so this is going to be 2/3 times by root 2/3 GA, this constant horizontal velocity, divided by the speed, so that's root 2GA, the hypotenuse. And just like before, the root GAs are going to cancel out. So if I do the cos inverse of what's left, I'll get beta equal to 67.3624. So the same answer as before, which is going to round to 67.4 degrees. This looks like slightly less working, but you choose the method that you're happy with, which you find easiest. So either using energy to find out what the speed is when it hits the ground, or using SUVAT to find the vertical part of the velocity when it hits the ground. Either way, we'll get an angle of 67.4 degrees, and I need to mention actually that 67.4 degrees from the horizontal, because I guess you could use an angle with the vertical. Let's just highlight that.